Hi everybody, so today we're going to be solving systems with inverse matrices. So let's get a few definitions out of the way so that we can understand inverses. So our first definition is multiplicative identity. And we have worked with multiplicative identities before with real numbers. We don't normally call it the multiplicative identity, but 1 is the multiplicative identity for real numbers because 1 times anything is itself, or anything times 1 is itself. So we'll write the multiplicative identity as any number multiplied by this is itself. Alright, so since 1 is the multiplicative identity for real numbers, we want a multiplicative identity for matrices because we're working with matrices. And the multiplicative identity for matrices is called the identity matrix. Now you can have a 2 by 2 identity matrix, a 3 by 3, a 4 by 4, a 10 by 10, and it all depends on what type of matrices you're working with. We're normally going to be working with 2 by 2 and 3 by 3s. So this is exactly what the identity matrix looks like. It's a 1 in the diagonal, 1's in the diagonal with 0's everywhere else. So this is a 2 by 2 identity matrix. A 3 by 3 would look like this. 1's in the diagonal, 0's everywhere else. And basically, the identity matrix is any matrix times this is itself, or this times any matrix is itself. So if we have a matrix A and we multiply it by the identity, it'll give you A, or the identity multiplied by A will give you A. So that's the identity matrix, standard, so make sure you remember it's 1's in the diagonal, 0's everywhere else. So our last definition, which is the most important, is our inverse matrix. And basically, when we're working with inverse matrix, so we have a matrix multiplied by its inverse equals the identity matrix. So if we're thinking in terms of like real numbers, if we have the number 4 and we want to know its inverse, so we would think in our heads, 4 times what will give us 1? And we all know that as a quarter, so the inverse of 4 would be a quarter. We want to know what the inverse of a certain matrix is. So if we have a matrix A and we multiply it by its inverse, it gives us the identity matrix. And this type of multiplication is commutative, so if you do its inverse times A, if you switch it around, it should still give you the identity. So there are some properties that we will find out along the way. So like every matrix doesn't have an inverse. First of all, only square matrices have an inverse, and there are other properties like if one row is a multiple of another, then it does not have an inverse. But for the most part, we're going to be working with 2 by 2 and 3 by 3 matrices that do have inverses. So all these definitions will make sense when we get into an example, so let's do that. So let's say we have a matrix A, 2, 1, 4, 3. And we want to find its inverse. Remember, inverse is denoted as a to the negative 1 or b to the negative 1, depending on what this is. So we want to find a to the negative 1, and we don't know what that is, so let's use variables. So I have a, b, c, and d. And the inverse is always the same size as the original. So, using our definition, a times a to the negative 1 has to equal the 2 by 2 identity matrix, and we're going to use this idea in order to find what a, b, c, and d are. So let's rewrite a times a to the negative 1, the inverse, has to equal the 2 by 2 identity. So now we use our matrix multiplication so that we can solve two sets of equations in order to find what specifically A, B, C, and D are. So let's do our matrix multiplication. First row times first column, 2A plus C equals 1, the 1, 1 entry. Then we have first row times second column, so that's 2B plus 1D equals 0 is our 1, 2 entry. Second row times first column is 4A plus 3C equals the 2, 1 entry, which is 0. And second row times second column is 4B plus 3D equals that 2, 2 entry. So now we have two sets of equations. This set has A and C. This set has B and D. I separated them for that reason. So now we can use simple algebra like elimination, substitution, to find out what exactly A, C, and B, D are. So I'm going to use elimination. I'm going to multiply the top by 2. So I will get 4A plus 2C equals 2. Now, I multiplied that by 2 so I can cancel out these A's here when I subtract the equations. So 4A minus 4A is 0. 3C minus 2C is 1C. 0 minus 2 is negative 2. So my C is negative 2. How do I find my A? Plug it back into either one I want. I'm going to do the top one. 2A minus 2 equals 1. Add 2 to both sides. So my A is 3/2. Do the same for this. Multiply this by 2 so I can cancel out those B's. 0 times 2 is still 0. Subtract both equations. 4B minus 4B cancels out. 3D minus 2D is 1D. 1 minus 0 is 1. So my D equals 1. Plug back into either one I want to find B. Subtract 1 from both sides. B equals negative 1/2 if I would divide by 2. So I found what specifically A, B, C, and D are. I found my inverse of A. Just make sure you're plugging back into the right position. So my A is 3/2. My B is negative 1/2. My C is negative 2. My D is 1. So the inverse of 2, 1, 4, 3 is 3/2, negative 1/2, negative 2, 1. And I found that by using variables to multiply these two, and they have to equal the 2 by 2 identity matrix. So let's solve a system of equations using the inverse, and I'm going to go on a brand new sheet of paper. So my example, so let's say I have this set of equations. Now, right off the bat, my variables don't line up, so make sure it's x, y, and then a number. And you can see that the problem is the second equation, so I'm going to rewrite 2x plus y equals 7. And I'm going to add 3y to both sides because I want x, y, and a number. So 4x plus 3y equals 6. So, step number 1, make sure they're in the right form. Step number 2, I need to write out my matrix equation so I can find what x and y equal. So I'm going to have a 2 by 2 matrix representing the left side of both of these equations, and it's 2 by 2 because I have two equations and I have two variables. My two variables are x and y. That's my column vector. Equals my answer, 7, 6. And then I fill this 2 by 2 matrix in by using the coefficients. So my coefficient here is 2 for x, 1 for y, and then the second equation is 4 and 3. And this is the same thing as that because you can see when you do multiplication, 2x plus 1y equals 7, 4x plus 3y equals 6. So I just basically rewrote it. So that's my step number 2. Now I want to solve for x and y. I want to know what x and y equal. And I'm going to solve for it using the inverse of this matrix 2, 1, 4, 3. And lo and behold, we have already found that inverse. So step number 3 is to find the inverse of your 2 by 2 matrix. So we need the inverse of our 2 by 2 matrix, which we have found already in the previous example. So that's 3 halves, -2, -1 half, and 1. So we are going to use this to find x and y, and we are going to multiply this inverse both sides of the equation on the left side. So I'm going to rewrite, I want to illustrate that for you. On the left side, I'm going to multiply the inverse. On both sides. And I want to do this because I want to cancel these two out. I want to solve for x and y. I want to get this column vector alone. So I cancel this out by multiplying by its inverse on the left side. So when I multiply these, I just get that identity matrix, which is basically 1. So I have x and y left on this side. And then what I have left here is this math that I need to do, this matrix multiplication. And I will just do that so I can find out what my x and y are. So I have this row times this column, 3 halves times 7, plus -1 half times 6. And then second row times the column, so it's -2 times 7 plus 1 times 6. When I do that, I have 21 over 2 minus 3, and then I have -14 plus 6. So I get x and y to equal 15 halves and -8. So x equals 15 halves and y equals -8. So I've used the inverse of this matrix so that it'll cancel out so that I can solve for my x and y. And remember, I'm multiplying on that left side. You can do the right side, but we're just working on the left side here to be consistent. So that's the end of our video, and we have learned inverses for 2 by 2 matrices and how to use them to solve a system of equations.